Electricity and magnetism are two of the most fundamental forces of the universe. But these two forces are actually connected. Yes, the force that attracts your hair when you rub a balloon on it, and the force that pushes or pulls magnets are actually intertwined. So, my name is Lucas, and today we're going to be talking about electromagnetism, inductors, capacitors, how electricity is generated and transmitted, and a bunch of other things related to electricity and magnetism in general. Electricity and magnetism are two sides of the same coin. That is electromagnetism. Electromagnetism tells us how charges and magnets interact with each other over time. So, we'll start out with a few experiments that you the viewer, can do at home to show the connection between electricity and magnetism. So for this first experiment, what you're going to need is an LED, two coils, a relay and a capacitor, and two breadboards and some jumper wires to connect it all. And of course, a 9-volt power supply or just a 9-volt battery. Although 5 volts does work, it works way less. It's not that good compared to 9 volts. So what you do is you make this circuit, and here's a schematic diagram if you really do want to build it. Pause now if you really want to build the circuit. And connect it to a coil, and then connect the LED to the other coil. So if we turn it on, and then we put this coil on top of the other coil, you can see the LED lights up. Oh gosh. Even though these two circuits are not connected, the LED still does light up. Now, you can have some problems with the connection points where the LED connects to the coil. So just double check that if the LED doesn't light up. So this is actually kind of how wireless chargers work, although they don't use this circuit to drive the coil. Meaning, you can actually take the LED circuit alone, put it on top of a wireless phone charger, and then you should get the same effect. So this next experiment is actually a bit dangerous because it involves high voltage. So please, just watch and don't do whatever you're gonna see next at home or in your friend's house or anywhere else, because it is pretty dangerous. Anyways, we take the same circuit from the wireless power transmission demonstration we did earlier, and then we connect it to a transformer. Now, it doesn't have to be a big transformer. It can be a small transformer you get from a wall adapter. But for this purpose, I'll just use this one because it's easy to wire up. And when we power the circuit, and then, of course, there. And then we take a look at the output of the transformer. You can see some pretty sweet arcs. Oh, dang it. So, there. You might say these arcs are pretty tiny, but really it's the high voltage breaking the air apart. So please don't play with high voltage, or else you're probably gonna get hurt. Let's do that one more time. Look at that. The electricity is breaking the air apart into plasma, the fourth state of matter. So if you take a single LED and a 1.5 volt battery and then connect them, I'm just using magnets to hold the wires to the battery. The LED doesn't light up. Why? Because an LED typically needs about 3 volts to turn on. So if you take 3 LEDs in series and then you connect the 1.5 volt battery, the LEDs now need 9 volts to turn on, and the battery can't do anything. But if you take a coil and then you attach it to the negative of the battery, and then the other side of the coil attaches to the negative of the LEDs, and the positive of the LEDs go to the battery, and then you short the LEDs, you suddenly get pulses of voltage that's high enough to turn the LEDs on every time you disconnect the wire. It's pretty interesting. Actually, if you replace the LEDs with, say, your finger, you can actually shock yourself a tiny bit. Which is, like, it's not that painful, but at the same time, it's pretty annoying. So you might know that moving a magnet around some iron filings will cause the iron filings to move. But you can actually do the same thing without a magnet, and you can just use a coil of wire. So let me demonstrate. So all I need to do is take a coil, preferably wrapped around a piece of metal that is ferromagnetic, and then attach it to a power supply. And so when I connect the thing, you can see that the coil attracts the iron filings, like so. The only downside to this circuit is that the coil gets pretty hot, and you'll have to unplug it. Gosh, something's melted. But anyway, you shouldn't let it run for too long because the coil gets hot and you could melt the wire. For this next one, what you're gonna need is a DC motor and two LEDs. Make sure the LEDs are wired in parallel, connected to the motor, and the LEDs are in reverse polarity. When I spin the motor one way, one LED lights the motor connection. One LED lights up. And when I spin the motor the other way, the other LED lights up, like so. Let's do that again. One way, the other, and the LEDs basically blink. So for the rest of these demonstrations, I wasn't able to recreate them successfully. So I'll let Mehdi from the channel Electroboom take it away and show you the demonstrations.
I've shown you before that neodymium magnets drop like a rock in air. But if you drop them through a roll of aluminum foil, they drop very slowly. Whee! But similarly, look, this frame is also made of aluminum, and my magnet has north and south on the surfaces, and if I put it on and let go, see, it goes down slowly. Magic! You can make a few turns of winding and connect an LED to its end and drop it on a wireless charger, and bam! Magic! You stick a battery on a magnet and short the battery using a piece of wire like this, and it starts turning. Magic! You connect two parallel reverse LEDs across a coil and pass a magnet through it, and ping pong, ping pong, ping pong, ping pong. Magic!
So, what exactly is going on with these experiments? Well, all of these experiments can be explained by the electromagnetic force, the force of the electric and magnetic fields. So in the 1820s, a scientist named Hans Christian Ørsted discovered that an electric current passing through a wire would reorient the magnetic needle on a compass. And another scientist named William Sturgeon noticed that by wrapping the wire around in a coil would strengthen the magnet generated by the electric current, and that by adding a ferrite or iron core to the coil, the magnet would become even stronger. They had just invented the electromagnet, a magnet that was controlled by electricity. Later, in the 1930s, another scientist named Michael Faraday discovered that by spinning a copper disc around the magnet, an electric current would be induced in the copper disc. He also noticed that when you passed a magnet in and out of a coil of wire, an electric current would be induced in the wire. He had just created the first ever electric generator by moving magnets around coils. He was also the first person to introduce the idea of an invisible electric and magnetic field. Later, he put two coils close together and noticed that when he pulsed an electric current through the first coil, an electric current would be induced in the second coil for a brief amount of time. He had also just created the first transformer. Later, he also connected electricity, magnetism, and light by passing a polarized light in front of an electromagnet. Because of his innovations and creations and ideas, he was named the father of electromagnetism. But sadly, no one believed him at the time, because he had never had a formal education and he did not know how to write the equations to describe these said fields. But eventually, another scientist named Clerk Maxwell wrote the equations of electromagnetism based on Faraday's observations. But Maxwell's equations predicted that a change in the electric field would generate a change in the magnetic field. And that change in the magnetic field would generate another change in the electric field. So what you get are these ripples or waves that propagate through space in the electromagnetic field. But later, Heinrich Hertz saw that these waves did exist, and that these so-called electromagnetic waves were actually what light was. But again, we'll get into that later. So, after all of these scientists and all of these experiments, we finally have four equations to describe how electricity and magnetism work. Now, these equations might look scary, but I'll break them down and explain them simply. So, apparently the video is getting pretty long already, so what I'm gonna do is I'm gonna make this a series of electromagnetism explained. What you just watched is part 1. In part 2, we'll be talking about Maxwell's equations, inductors, and capacitors. And maybe, if we have enough time, we'll talk about inductance and capacitance, the math behind both of them. And in the next parts, we'll be taking a look at how electricity is generated, motors and generators, transformers and wireless power, Lenz's law, the Philippine power grid, electromagnetic waves and wireless communication, eddy currents and electromagnetic levitation methods, which will include superconductor levitation and magnetic rivers, and finally the conclusion. Anyways, if you watched the entire thing, thank you so much. And if you find any imperfections or mistakes, please let me know in the comment section below. I too want to learn. Anyways, I don't really know when part 2 is going to be coming out, but stay tuned. Anyways, bye.